Hey there, welcome back to the channel. So in today's video, we will be proofreading the realloc function because let me show you. So if I do this verbose output, take a look at this. So this is 97% performance considering the throughput. Sorry, this is the utilization and throughput. You might be wondering, how is my utilization 107%? That is theoretically impossible. Well, that is because of this. This is because the trace file 9 has a lot of realloc calls, and I think that is causing something to go above 100%. So let's just proofread it. I think I am returning. So what I think is I am returning some kind of like a garbage pointer, and it is getting freed. So this is what I assume it's happening. So let's proofread it. So yeah, void my realer we take. So here we get a pointer. The pointer is a pointer to the original block. And well, by the way, don't forget the pointer here is actually the pointer at the start of the space, not of the whole block. So we get this, and then we get the size, and then we align it to get the point. Yeah, as you can see over here, the pointer is not directly the start of the block. It is the start of the space. To get to the start of the block, we have to move behind by one header. So that's what we do over here. And then block size is actually block size, and this is for getting the actual block size because we have um like LSB, we have set LSB. So if the size value is odd, that means if the size value is odd, that means the block is allocated. If it is even, that means the block is free. So to get the block size, so this is definitely a allocated block. So we are just removing the LSB from it. We are performing an AND operation on negation of one. So yeah, cool. So the difference is here the difference, what this difference means. So difference in this video, it's mostly like the rubber duck. Wait, let me show you. Yeah, okay. Rubber duck coding, something like that. Yeah, rubber duck debugging. So what that means is that uh, programmers keep a rubber duck beside them and they explain it to the rubber duck like what the code is doing. Uh, this is some concerned right line quack. Okay, so yeah, I you can say I'm kind of like a subscriber debugging, you can say. Most of the very high probability is that you're new to this channel, so welcome to this channel. And yeah, you can say viewer debugging. Yeah, so I'm doing viewer debugging. So let's get into it. So size difference. What this difference means over here is that this difference is the entire block that will be left if we complete this. So let's say our block size is 100 and the size that we have to allocate is 50. Well, now that you think of it, the block is already 100 bytes, and the new size that we want is actually just 50 bytes. So we don't need to allocate a new block, right? Because the block, which was of 100 bytes, now the process is demanding a lesser block. So the size has shrinked. So we don't need to move anything anywhere. We don't have to call anyone. So what that means is that we have to just shrink this allocated block, and what the remaining block is, we have to split it and make it a new free block. So that's what we do over here. If the difference happens to be greater than or equal to 0, which means the block size is greater than align size, that means the size has been shrinked. If it is like this, then oh, this now difference, split block, align size. Yeah, yeah, yeah. Yeah, cool. So difference is greater than or equal to zero, and difference. So if the difference is at least, well, if it is positive, that means the size has shrunk, and the difference is at least header plus footer. What that means is that the difference, so the smallest free block that can be present is just header and footer. The size values inside it will be zero. So the smallest block is just header plus footer. So if it is at least header plus footer, the difference that is the the remaining block remaining, then we can say that we don't need to give the entire process, like the entire thing to it, right? If the process is asking for 50 bytes and we have a block of 100 bytes, we shouldn't allocate, like we shouldn't give it a block of 100 bytes. It doesn't feel right because that is internal fragmentation, you know. So we will split the remaining 50 bytes and we will make it a new free block and add it to the free list. So that's what we do over here. So the void allocated space. So this is a split block function. What it does is that it takes the current pointer of the block, well, the start of the entire block. It takes in align size, which is the size that we have. Sorry, I mean the size that we want of the allocated block. And the difference is the difference, that is like the total block that will remain. So if I show you this function, where should I show you this? Yeah, let's do it. This is 490, right? Okay. Yeah. So split. Yeah. So this is the split block function. What it does over here is that we get a block, we have allocated size, and we have difference. So this was supposed to be aligned size, if you remember. So the useful space is actually we cannot utilize the entire difference, right? As I said, difference is the entire block remaining. We have to reduce the header and footer from it to get the actual usable space. And the values useful space over here, it is allowed to be zero. It's fine. It just cannot be negative. So header block allocated header will be at the starting of the block. That's correct. Allocated footer will be at block, okay, plus header, okay, and the allocated size. Correct. Allocated header size is correct. This is fine. Allocated header next will be null. Since it's an allocated block, allocated blocks don't have previous and next values, so it will just point to null. The split header will start from after that. So allocated footer plus footer. So this is the start of the block. So split footer will be split header plus header. Yep. And the useful space. Correct. Split header size will be useful space. Useful space. This is fine. Yep. I think this function is cool. So next are the previous value. Yeah. By the way, look at this. So this is the next value. So the since it's a split block, since the block has been split, we will be adding it to the free list. So now its the next pointer will point to the start of the free list, and then if free pointer is not equal to null, if the free pointer is not equal to null, that means there is at least one block inside the free list, then we have to change its previous pointer. So its previous pointer will point to the current split header, and then free pointer will be set to the new split header, which is the new block. So the new block has been successfully added. The allocated space will be allocated header plus header forward, which was, yep, correct. And then we return the allocated space. So allocated space is what the split block function has returned. If you go over here, yeah. So this is the allocated space, and then we return the allocated space. So yeah, cool. Else if the remaining block is not header plus footer, that means the block has shrinked, but it is not header and footer. So like it is not, we cannot make it a free block. So let's say the minimum space needed for a block to be free block is actually 32 bytes. So header is 24 bytes and footer is 8 bytes. So the minimum space required for a block, a free block, is 32 bytes. So what if the block has only 24 bytes left? Well, we cannot make a free block out of it, right? So we will just, yeah, fine. That kind of, that small, that is 32 bytes is negligible unless the allocated space is 8. Hmm, it's fine. We will be writing better memory allocators in the future. Bind free list and trees and other things. I'm going to try that, but I'm not sure on that. But yeah, let's get going. So difference is at least greater than zero, greater than or equal to zero. We just return the pointer, which was this space. This is the space, and we just return it again. So that's fine. So here we check if the left and right blocks are free. So if here we get the values, so let's get to these functions. So left free, yeah, let's get to left free must be over here. Yeah, nice. So left free gets a pointer. So this pointer is the you can say, yeah, just a minute. Hey there, I'm back again. Oh, sorry. So yeah, we were over here. So this is the left free block, and here what we will do is that, okay, so this pointer is actually the space pointer. It's not the block one. So to check if the adjacent left block is free, what do we have to do? Well, we are at the space pointer, so we have to move by header behind. That's cool. And then we have to move footer behind. So by doing this minus footer, we are in the territory of the left block. And if we cast that into a footer block pointer, then we get the footer block pointer of the left block. And yeah, this is the condition where we check that we are not um, crossing into the, what is that called? A DSS, something, data segment, something. It is below the heap. I don't remember. Let me search. So heap and stack diagram. Yeah, uninitialized data. Okay, my bad, my bad. There was a better diagram. Oh yeah, yeah, BSS. What was that? Full form of BSS? I don't remember. Oh, I messed up. Block started by symbol. Yeah, something like that. Yeah, used for uninitialized data such as global and static variables. Cool. So that's fine. And then yeah, okay. So this is fine. Sorry. This just checks like we are not inside the territory of the, like we are not crossing the heap boundary. So it will just return false. Like we cannot say that the left block is free if it is going beyond the heap boundary, right? So we should just return false, that okay, there is no free block on the left side. So that's what we do over here. Then we get size t value if we are not at the boundary. So we get the left block size value from this, and then we check if the left block size. This condition shouldn't be there, right? I don't need this condition. Yeah, okay. How about we check this? So We haven't made any change, right? Yeah. Okay. Make, yeah, we didn't do any changes. So let's test this. So let's say m driver dash v. So we get a value. Yeah, whatever. This is definitely fake. But yeah, let's take a look at the utilization. Let me do that once more. 88, 89, 89, 79, 57, 99, 69, 88, 71. Yeah, this pretty much stays the same. So let me write that down, and then I will do one more change and we will check like is it changing. So 88, 89, 89, 79, 57, 89, 79, 57, 99, 69, 88, 99, 69, 88, X, and 71. Okay, so now let us do the change. This should, what we say, this should do some magic. Maybe not because there might not be any zero-sized blocks. But let's, what's wrong in testing that theory. And let's also do this for right block size too. Oops. Yeah. So let's test this. Make m driver dash v. 88, 89, 89, 79. Oh, 79 changed to 80. That is negligible, I hope. So yeah, 57, 99, 69, 69 changed to 65, so the utilization dropped. 88 and 71. So we can't conclude anything, but it's working, so we'll keep it. Sure. Let this be. Because even if it's a zero block, we still can utilize the footer from it or the header from it, 24 bytes, easy money. Yeah, okay. So let's keep going. So here we check if it is mod 2 equal to 0. This is, I hope compiler optimization does its stuff, so we don't have to check, do some, well, if I were to do this, we will perform like, uh, what is it? And one, right? Left block size and one. This will tell us like if the LSB is set to, like if the LSB is one, and then we can negate that, or we can do and negation of one. That's easy and return to. But I think the compiler optimization does its stuff. So if this is even, then we will return to. That means the block is free. And if it's not, return false. Easy. Let's take a look at write free one. So we are at current block. So this is the space pointer. Current is pointer minus header behind. Cool. We get the block's current size. We remove the LSB, and then yeah, block size we get over here, current size, and then write block is actually the pointer plus block size plus footer. Then we get to the start, like we are at the right bound, we are at the correct boundary of the right block and the current block. So this is the boundary between them, and then we cast this into a header block. Cool. And if right block happens to be greater than mem heap high, so it is again exceeding the heap boundary, then it returns false. And size t, right block size, is actually, yep, size. And if it is even, we'll return true, and if it is not, we'll return false. So this is fine. So we did this, left free blocks. We have over here the new space. This is the actual answer. So this is so this logic, this entire logic that is present below this. So this entire logic is for when the block is actually growing. So left and right block, we get if they are freed or not. If none of them are freed, then we go over here and we just say call my malloc and allocate this block. So what happens? So here we get like the left block is not at all free, and here we get the right block is not at all free. So what do? Our current block as we checked over here, cannot satisfy the growth, right? It is not like the difference is definitely greater than uh, sorry, the difference is definitely smaller than zero, which means the new size that they want is actually greater. So what do? We call the copy block. So we need a bigger block. So for a bigger block, we need copy block. What copy block does, it just calls my mallet, nothing much. So current header, this is the my free, right? Yeah, cool. So what it does, copy block, it gets the current header, which is, oh, why do I have this over here? Was it working like this? Huh? Okay. So the current header is header block. So pointer is the space one. Again, don't forget. See, take a look. Let me also make sure. So pointer, yeah, we are passing pointer most of the time. Yeah, cool. So the pointer over here is actually the space one. So we move header behind. We get the current block's header, header block. We get the current block size, so current size, and we remove the LSB. Void new pointer. We get the new pointer. We call mymalloc for the new size that we want. And yeah, now that I remember another thing, which is we should be passing size at these places. It should be aligned size, not size. Let me just cover this copy block function, and then I will make sure that this doesn't happen again. Okay, so we get the new pointer size. If new pointer is equal to null, return null. We copy this. So the new pointer that we get, it is also the space one. Remember, my malloc returns the space one. So we get the new space, we have the previous space, and how many bytes do we want to copy? Well, current size. Why current size? Because the new block that we have, it is bigger. So we want to copy the smaller stuff. So current size is the smaller one. So boom, we copy that. Okay, yeah, cool. If the block was shrinking, then we won't copy the bigger one because what will happen is that also we shouldn't say bigger and smaller. It's just what is appropriate one. We have to copy. So our previous block is getting destroyed. So we have to somehow, you know, so we have to somehow take care of like copying the current size, and we will free the pointer. So this is the oh, my free pointer also accepts the space one. Yeah, cool. So pointer, yeah, current size is fine. Yeah, current size, we copy this and we return the new pointer. New pointer is the space one. We return this and then we over here we have new space set. Cool. So here let's get to this and now the stuff gets interesting. So what coalescing RL does is that coalescing RL, so the else if condition. So left free and right free both happen to be free. Like the both adjacent blocks are free. Well, we definitely need to merge them first. Let's merge them. So we merge them, and what do we find out? Well, we find that coalescing RL we merge, and this void pointer that we get is supposed to be the what is coalescing RL? I forgot. So we are passing. Let's just take a look. So we are passing a free pointer and the normal pointer, the space one. Okay, let's take a look. So coalescing RL. Free pointer, current header, size, skip block, zip block, sure, total size, left size, header block, new block, left header. What's the start of the block? So this will return the start of the block. So yeah, cool. So this will return the start of the block, not the space. So we go over here again. So this is the start of the block, the current RL. and then we call the coalesce copy function. We pass it current RL, we pass it pointer, we pass it block size, and then we pass it size. So we pass it current RL. Let me reduce this. I'm sorry if this is not visible. I think it might be decently visible to you guys. So we pass it to coalesce a copy function. Yeah, now it's visible. So we call it over here. So we pass it, we call current RL. Sorry, my bad. Yeah, okay. So we pass it current RL, the merge pointer. This is start of the block, remember? Current RL is the start of the block. Yeah, okay, okay. This is merged space. Yeah, sure. So yeah, we go here. Current RL is the start of the block. Copy from, how much to copy? Well, the block size is present over here. And the size is the size. Well, what is size? Coalesce. Wait, okay, okay. Merged space we have over here. We are copying merged space, and we have to copy from to the merged space. And how much to copy? Well, the block size, because the block is increasing. Okay. We do this. We move this from over there to this. Now we have to split it. So header block. Yeah, okay. So merged header is merged pointer. Cool. And then split difference is merged header size minus size. Okay. This should be a line size. Let's try sending a line size for each of them, because I think that is the correct thing that we should send. I still don't remember why did I write a line, why did I write size? What is size doing? So size is the difference thing, right? We are using it for difference. Hmm. So size we are sending in. Size denotes what is the current blocks, like what is the size supposed to be. Like this is what the size is supposed to be of the block that we want, and this is over here, and the split difference is this. Cool. And this is correct. Yeah. Okay. Okay. Cool. So I hope this should work. Let's make. Let's do this in driver dash v. Yeah, nothing much changed. Make m driver dash v. If I do g, it's the same thing. Yeah, nothing much. 88, 89, 89, 80, 57, 99, 65, 88, 105, and 71. I do think I know what why the 1500 is happening, but now that I'm not sure. Should we fix that first and then get back to our stuff, or what should we do? Like, should we fix that first, or should I continue doing the optimization that I have in my mind for Coalesce? So what optimization I have for realloc in my mind is that if the block that we want to reallocate is at the end of the heap, so we don't need to call, uh, you know, so we don't need to call, We don't need to call the what do we say? I mean, yeah, we still do need to call it. Hmm. Okay, this is getting a bit okay. So if we so the block, if the block needs to increase its size and it is at the end of the heap, then we will call mymalloc. And if mymalloc returns null, that means like traverse free list. If traverse free list returns null, yeah, we will call traverse free list. If traverse free list returns null, that means it did not find the appropriate size of the block. Then we can just call memsbrk directly, and we will not allocate the entire size. We will just allocate, like we will just ask for extra size that we want. Like let's say our block is of 100 bytes and it needs 200 bytes. We won't call memsbrk for 200 bytes. We won't call sbrk for 200 bytes. We'll just call it for 100 bytes because our block is at the end of the heap. And if we call sbrk for 100 bytes, it allocates this, and we can just eat it up entirely. We'll just our block will eat it up, and boom, we have 200 bytes. So that's what I have in my mind. So this is when this I have to add a condition over here. Uh, Coalesce. I do need to add that condition over here. I do realize something right now. Oh boy! I found the bug. Nowhere am I checking that. Okay, fine. Left and right blocks are free. Fine. But are they enough? I'm not checking that at all. And I should check it. I added that in the previous code, but I removed it. Okay. Okay. Fine. Add conditionals to check. Add conditionals. Let me write that on whiteboard, I'll remember that stuff. So add conditionals in realloc to check for total size. To check if total size is enough. If left plus current plus right is enough. Boom. I think we have our culprit. So yeah, that is what is happening. It is overwriting the blocks, and that is, damn it. It is overwriting the blocks. Yep, we are going to fix that in the next video. Yep, 33 minutes. This is by far like the second smallest video. The first might be, which one might it be? Might it be? Seriously? That is very bad English. Okay. So, the smallest video on my channel will be, well, we have one of 34 minutes. So 34 minutes, 19 November. The 29th video is the smallest one, I guess. It's of 34 minutes. I don't think there is anyone smaller than that. Hmm. Yep. Oh, oof. Now this is the smallest, this is the second smallest video. Now, nice. So yeah, thanks for watching this video. I'm Aditya Pacharne and I'm an engineer for fun. Sorry, I did not say that clearly. I am Aditya Pacharne and I am an engineer for fun. Bye.